Hi guys, this is the EdExcel A-Level Further Maths Paper 2 from the June 2019 series, and this covers the Core Pure Maths section. Okay, now do make sure you've got access to the formula book and also a calculator. I recommend using this Casio ClassWiz calculator. Okay, so in terms of the examiner's report, I personally thought this paper was quite difficult, but I think this paper, as the examiner report says, it differentiated between candidates and it tested people at all abilities. But let's take a look at each question in turn. Question number 1. We have to prove that the inverse of hyperbolic tan of x is equal to 1/2 times by the natural log of 1 plus x over 1 minus x, where x is in between minus k and k, and we have to state the value of this constant k. First of all, we begin by setting the inverse hyperbolic tan of x equal to y. Okay, and then if we take the hyperbolic tangent of both sides, you'd find x to equal the hyperbolic tangent of y. Okay, and this of course is the same as the hyperbolic sine of y over the hyperbolic cosine of y. In an equivalent form, this is the same as 1/2 times by e to the power of y minus e to the minus y over 1/2 times by e to the power of y plus e to the power of minus y. And happily, you'd see that these 1/2s cancel on the top and the bottom. So we have e to the power of y minus e to the power of minus y over e to the power of y plus e to the power of minus y. And we can rewrite this bit by multiplying through by e to the power of y, and therefore you'd find this is the same as e to the power of 2y minus 1 over e to the power of 2y plus 1. Okay? Having done that, let's now multiply both sides by e to the power of 2y plus 1. So we have x lots of e to the power of 2y plus 1 equals e to the power of 2y minus 1. And if we expand the brackets, on the left hand side we have x times by e to the power of 2y plus x, and this is equal to e to the power of 2y minus 1. And if we gather everything containing an e to the power of 2y on one side and everything that doesn't contain and e to the power of 2y on the other side, we have e to the power of 2y minus x lots of e to the power of 2y equaling 1 plus x. And on the left hand side we can factorize out an e to the power of 2y. So we have e to the power of 2y lots of 1 minus x equals 1 plus x. And if we divide both sides through by 1 minus x, we have e to the power of 2y equals 1 plus x over 1 minus x. Okay, and then if we take the log of both sides, 2y is equal to 1 plus x over 1 minus x. The natural log of this, 2y equals the natural log of 1 plus x over 1 minus x, and dividing both sides by 2, y is equal to 1/2 times by the natural log of 1 plus x over 1 minus x. And we already know that y is equal to the inverse hyperbolic tangent of x. So therefore, the inverse hyperbolic tangent of x is equal to 1/2 times by the natural log of 1 plus x over 1 minus x. Okay? And this is valid for values of x being in between -1 and 1, and therefore k is equal to 1. Okay? Now for part B, hence or otherwise, we have to solve the equation 2x equals the hyperbolic tangent of the natural log of the square root of 2 minus 3x. So to do this question, part B, we have 2x equals the hyperbolic tangent of the natural log of 2 minus 3x square rooted. And if we take the inverse hyperbolic tangent of both sides, we have the inverse hyperbolic tangent of 2x equaling the natural log of 2 minus 3x square rooted. Okay, and if we use what we had in part A, the inverse hyperbolic tangent of x is equal to 1/2 times by the natural log of 1 plus x over 1 minus x, and so if instead we have a 2x instead of an x, the inverse hyperbolic tangent of 2x, that will equal 1/2 times by the natural log of 1 plus 2x over 1 minus 2x. Okay, and this of course is equal to the natural log of 2 minus 3x to the power of 1/2. And the reason I write 2 minus 3x to the power of 1/2, of course we can power slide this 1/2 to the front, so we have 1/2 times by the natural log of 2 minus 3x. Okay, And the reason I want to do that is if we of course take a look on both the left hand side and the right hand side, what you'd find is the halves first of all cancel, and if we anti-log both sides, we have 1 plus 2x over 1 minus 2x equaling 2 minus 3x. Okay? And therefore, we can now solve for x. We can first of all begin by multiplying both sides through by 1 minus 2x. So we have 1 plus 2x equals 1 minus 2x lots of 2 minus 3x. And if we expand and simplify, we have 1 plus 2x on the left hand side. On the right hand side, we have 6x squared minus 7x plus 2. And if we take everything over to one side, 6x squared minus 9x plus 1 equals 0. We wish to solve this quadratic equation. So if we solve this quadratic equation, we have x equals minus 9 plus minus 9 squared minus 4 lots of 6 lots of 1 over 2 lots of 6. Okay, so what you'd find inside the bracket, we get 57. So you'd find x here to equal 9 plus minus the square root of 57 over 12. Okay? And if we take a look at what values of x this thing on the left is valid for, that's valid for x being in between minus 1/2 and 1/2. Okay? And therefore 9 plus root 57 over 12 is bigger than 1/2, and so the value we wish to choose is x equals 9 minus root 57 over 12. Okay? Now in terms of question 1, where we had to show this result, that produced a number of mixed responses. A lot of people were able to obtain an appropriate equation in exponentials, but did not appreciate the need to rearrange it, particularly those who did not introduce another variable. And when it talks about producing another variable, my other variable is y. Those who did make e to the 2y the subject usually did so correctly, although a few did not convert the resulting into the required. Some solved a quadratic in e to the y, but often got bogged down in the algebra. I think that's on about this bit over here. But there were a few attempts to use the inverse hyperbolic sign over the inverse hyperbolic cosine for the inverse hyperbolic tangent, and I thought that was quite an obvious result to use because everything drops out nicely otherwise, and then you can rearrange easily. And there were a couple of people who forgot to state the value of k. It says in the question, state the value of k. And for part B, what could I say about part B? That was more successful, but I mean, it's all easy stuff because you can end up with some sort of a quadratic, as we do here. And when you solve your quadratic, obviously you'll produce a positive and negative solution, but because of the restriction, you have to neglect all of those values. And one other problem that was in this question, instead of writing tan h, a lot of people wrote tan instead, even though tan h was intended. So just be a bit careful over there. Question number 2. The roots of the equation x cubed minus 2x squared plus 4x minus 5 equals 0 are p, q and r. Without solving the equation, we have to find the values of the following. Well, I think at this point it would be a good idea if we state the values of a, b and c and d. Clearly, a is equal to 1, b is equal to minus 2, c is equal to 4, d is equal to minus 5. And the first thing we can do, we can find out the sum of the roots. P plus q plus r is equal to minus b over a. So we have minus minus 2 over 1, which is 2. We can now find the pair sum. PQ plus PR plus QR is equal to C over A. 4 over 1 is equal to 4. And now we can find the product PQR, that's equal to minus D over A. So we have minus minus 5 over 1, which is 5. For the first part, we have to find out what 2 over p plus 2 over q plus 2 over r is. And what you'd find is all this is equivalent to 2 lots of PQ plus PR plus QR over PQR. Okay? So we have 2 lots of 4 over 5. Okay? So we have 8 over 5. Hopefully that makes sense. And for the next part, we have to work out p minus 4, lots of q minus 4, lots of r minus 4. So we have p minus 4, lots of q minus 4, lots of r minus 4. So if we expand the first 2 brackets, we have pq minus 4p minus 4 lots of q plus 16, and then we still multiply this by r minus 4. If we multiply all these terms together, we have pq times by r, so that's pqr. pq times by minus 4, that would be minus 4, that would be minus 4 pq. And then we have this times by this, So then we have minus 4 PR, and then we have this times by this, so we have minus 4 QR, and then we have 16 times by R, and then we have minus 4p times by minus 4, and then we have minus 4q times by minus 4. So we have 16p plus 16q plus 16r, and then we have 16 times by minus 4, which is minus 64. And if we collect all the terms together and factorize, we have pqr minus 4 lots of pq plus pr plus qr, and then we have 16 lots of p plus q plus r, and then we have this minus 64. So we have 5 minus 4 lots of 4 plus 16 lots of 2 minus 64. You'd find we get minus 43. And finally, we have to work out p cubed plus q cubed plus r cubed. Okay, so we have p cubed plus q cubed plus r cubed. Well, what this is the same as is a standard result, which you should know. That's the same as p plus q plus r cubed minus 3 lots of p plus q plus r lots of pq plus pr plus qr plus 3 pqr. It's a standard result which I recommend you all go over. And if we work this out, we have 2 cubed minus 3 lots of 2 lots of 4 plus 3 lots of 5. It turns out we get minus 1. Question 2 was talking about the roots of this cubic polynomial, and then from there we had to find out these various different results. Sign errors were rare, which is good, and it was easier if we begin to find out the sum, the pair sum, and the product. And that's exactly what I did over here. If you do that, that makes the rest of the question easy. The first part was quite easy. The most common method was the method I chose to use. But the alternative method was to use a substitution. The other part was quite easy because you can just expand and simplify, and then hopefully you can recognize you've got the product, the pair sum, and the sum, and you just plug in the numbers that you found in here. And the last part was a bit more difficult, and that's because a lot of people fail to recognize this relationship here. So just make sure that you know that relationship. And because of that, a lot of people were unsuccessful in this part of the question. Question number 3. We have f of x, which is equal to 1 over the square root of 4x squared plus 9, and using a substitution we have to show using a substitution that should be stated clearly. We have to show that the integral of f of x with respect to x is equal to a times by the inverse hyperbolic sine of bx plus c, where c is an arbitrary constant and a and b are constants to be found. So in this question, for part A, we're looking at the integral of 1 over 4x squared plus 9 square rooted with respect to x. Now, if you look at the final answer, we have an inverse hyperbolic sine. And if you go to the formula book, hopefully you'll find under the integration section where we have the inverse hyperbolic sine. That's over here. Perhaps if I highlight this, we would at some point have to use this result over here. And the reason for that is because in the question we had an inverse hyperbolic sine. So if we integrate 1 over the square root of a squared plus x squared, we get the arc hyperbolic, we get the inverse hyperbolic sine of x over a. Here we have an x squared, and in the question we have a 4x squared. If somehow we have an x squared here instead of a 4x squared, we can quite easily use this result. And we can do that by making the substitution of x equaling a half u. So in this question, if we let x equal 1/2 u, dx over du, that's equal to 1/2. From which we can see dx is equal to 1/2 du. And if x is equal to 1/2 u, we can of course see u is equal to 2x. And so this integral would become the following. So the integral becomes, we have the integral of 1 over, well, instead of us having an x, we want to replace the x with 1/2 u. And notice if we square u, we'll get 4x squared. So here we'd end up with u squared. And then we still have this plus 9. And then we square root. And then dx, that's 1/2 du. So we multiply by 1/2 du. Okay? And this then over here is equivalent to 1/2 times by the integral of 1 over u squared plus 3 squared square rooted with respect to u. And if you go here, if you take a look over here, that's of this form. So therefore, the result of this is 1/2 times by the inverse hyperbolic sine of u over 3. And we know that u is equal to 2x. And therefore, this integral, if I just write that down, this integral is the same as 1/2 times by the inverse sine of 2x over 3 plus c. Okay? And therefore the values of a and b, the value of a, if we take a look, that's equal to 1/2, and the value of b is equal to, if we take a look, the value of b is equal to 2/3. Okay? And now for part b, we have to find an exact form in terms of natural logarithms, the mean value of f of x over the interval 0 to 3. Okay. So the mean value is equal to 1 over b minus a lots of the integral of f of x with respect to x between the limits a and b. So what we have then is the mean value equaling 1 over 3 minus 0 lots of the integral from 0 to 3 of 1 over 4x squared plus 9 square rooted with respect to x. And we've already found out what this integral was, so we have 1/3 lots of 1/2 times by the hyperbolic, the inverse of the hyperbolic sine of 2x over 3. Okay, let's just close this bracket off, between 0 and 3. Okay? So if we substitute in our limits, for the upper limit, inside this bracket we have 2 times by 3 over 3, which is 2. And for the lower limit, if we substitute in 0, the entire thing will become 0. So we have 1/6 times by the inverse of the hyperbolic sine of 2. And we wish to write this result in terms of natural logarithms. And if you go to the formula book, somewhere in the formula book, the inverse sine is given here. The inverse sine of x is equal to the natural log of x plus the square root of x squared plus 1. So if we write that down, we have 1/6 times by the natural log of 2 plus 2 squared plus 1 square rooted. So we have 1/6 lots of the natural log of 2 plus the square root of 5, which is our final answer. In terms of the third question, where you basically had to evaluate this integral, well, first of all, you're given a clue in the question on how to approach this. You've got the inverse hyperbolic sine to use in this question. You can use the formula book, but required integration by substitution to do this question. Okay, so just be a bit careful, and then from there you can obviously use the formula book. Obviously arc hyperbolic sine is the same as the inverse hyperbolic sine. But other than that, it was just a standard integration by substitution problem. For the next stud, which is quite good, a few errors were seen in the use of the logarithmic form of the inverse hyperbolic sine, even though I did use that myself. But generally the 2 marks here were widely scored. Question number 4. The infinite series C and S are defined by C equals cos theta plus 1/2 cos 5 theta plus 1/4 cos 9 theta plus 1/8 cos 13 theta, and S is defined by sin theta plus 1/2 sin 5 theta plus 1/4 sin 9 theta plus 1/8 sin 13 theta, etc. Given that the series C and S are both convergent, we have to show that C plus IS equals 2e to the power of I theta over 2 minus e to the power of 4I theta. So to do this question, if we work out C plus IS, C plus IS, that's equal to, well, if we add these together, C plus IS, we have cos theta plus I sin theta. Remember, we have I times by S. And then we have 1/2 lots of cos 5 theta plus I sine of 5 theta. And then we have 1/4 lots of cos of 9 theta plus I sine of 9 theta. And then finally, we have 1/8 times by cos of 13 theta plus I sine of 18, I sine of 13 theta. And then we have other terms as well. And if we use de Moivre's theorem, what all this is the same as, is cos theta plus I sin theta plus 1/2 lots of cos theta plus I sin theta to the power of 5 plus 1/4 cos theta plus I sin theta to the power of 9 plus 1/8 cos theta plus I sin theta to the power of 13, and then we have higher order terms. And if S and C are both convergent series, then we can model this as a geometric series to infinity, because essentially the terms continue to grow. So let's write that down. C plus IS is a convergent geometric series to infinity. Okay, and if we go to the formula book, under the regular A-level math section somewhere, here, the sum to infinity for a geometric series, we have A over 1 minus R, for the mod of R being less than 1. Let's write that down. The sum to infinity is equal to A over 1 minus R, where the mod of R is less than 1. Okay? So you'd find our first term is equal to this thing over here. So our first term, A, that's equal to cos theta plus I sine theta. Okay, that's this term over here. And the common ratio R, that's equal to, well, in terms of the numbers, each time we multiply by a half, and then we also multiply by cos theta plus I sine theta to the power of 4. Okay? And hopefully you can recognize that by looking at these successive terms. Having said that, substituting back into this formula, C plus IS is equal to A, our first term, cos theta plus I sine theta over 1 minus R. So we have 1 minus 1/2 of cos theta plus I sine theta to the power of 4. And if we multiply through, well, we can actually use Euler's relation to rewrite this. We can rewrite this as e to the I theta over 1 minus 1/2 e to the I 4 theta. And if we multiply through by 2, we have 2 ei theta over 2 over 2 minus ei to the 4 theta. And that's the result we wanted to show. And now for part B, hence show that S is equal to 4 sine theta plus 2 sine of 3 theta over 5 minus 4 cos of 4 theta. Bit of a difficult question. So for part B, we already know that C plus IS is equal to 2e to the I theta over 2 minus e to the I 4 theta, which is the same as from here, cos of theta plus I sine theta over 1 minus 1/2 of cos theta plus I sine theta to the power of 4. And if we multiply the top and bottom by 2, and then if we use Demois's theorem for cos theta plus I sine theta to the power of 4, this bit is the same as cos of 4 theta plus I sine of 4 theta. Hopefully that makes sense so far. And if we expand the brackets on the top, we have 2 cos theta plus 2i sine theta, and on the bottom we have 2 minus cos 4 theta plus I sine of 4 theta. And essentially, with this, to do this question, to show that we have S equals something, if we rationalize the denominator to get rid of the I at the bottom, we can then compare the imaginary parts to work out what S is. So in terms of what we have here then, is all we have to do with this 2 cos theta plus 2i sine theta, we would have to multiply the top and bottom by the complex conjugate of the bottom. So we have 2 minus cos 4 theta plus I sine of 4 theta on the bottom, and therefore we multiply the top and the bottom by 2 minus cos of 4 theta minus I sine of 4 theta. Okay? Hopefully that step makes complete sense. So let's just finish writing this down. And when we multiply these together, the i's on the bottom will disappear. So the next couple of steps are quite long. Here we have to do a lot of expanding. 2 cos theta times by 2, that's 4 cos theta. 2 cos theta times by minus cos 4 theta, that's minus 2 cos theta cos 4 theta, and then 2 cos theta times by minus I sine 4 theta, that's minus 2I sorry, my mistake, this is a minus, and therefore this is a plus. Okay, so the minus into the bracket gives this, that was my mistake. So this becomes a plus as well. So we have 2I sine 4 theta. Okay? Hopefully that makes sense. Just be careful when you expand the brackets. Okay, so now I've multiplied those together. And then we have the other 3 terms. We have 2I sine theta times by 2. That's 4I sine theta. And then we have 2I sine theta times by minus cos 4 theta. That's minus 2I sine theta cos 4 theta. And then we have 2I sine theta times by I sine 4 theta. You have to be careful here. You would have to recognize that essentially you have to remember in this question I is equal to the square root of minus 1. So I squared is equal to minus 1. So we have I times by I, which is I squared, which is minus 1. So we have minus 2 sine theta times by the sine of 4 theta. So that's everything we have on the top. Okay? Now on the bottom, we have a difference of 2 squares. We have 2 minus cos 4 theta squared, and if we work that out, that would be 4 minus 4 cos theta, 4 cos 4 theta, plus cos squared 4 theta. Okay, so that bit, this bit over here, comes from multiplying this bit with this bit, and then we have minus I sine 4 theta times by I sine 4 theta. Well, minus I times by I, that's minus I squared, so that's minus 1, so that would be plus 1, and then we have sine squared of 4 theta. Okay, so on the top, if we rewrite the top, we have 4 cos theta plus 4i sine theta minus 2 cos theta cos 4 theta minus 2 sine theta sine 4 theta and then we have plus 2i sine 4 theta cos theta minus 2i sine theta cos 4 theta. Okay, so I've just grouped the terms together. Okay, so let's just draw our fraction line. On the bottom, be a bit careful. Cos squared 4 theta plus sine squared 4 theta, that's just 1. And then we have 1 plus 4, that's 5. So we have 5 minus 4 cos of 4 theta on the bottom. And if you take a look over here, we would now have to compare the imaginary terms to find out what s is. So now compare imaginary terms. Okay, so on the left hand side, of course, we'll just have this s, and everything that contains an imaginary term, we have this bit, and then we have this bit, and then we also have this bit over here. Okay, so s is equal to, if we now compare imaginary terms, s is equal to 4 sine theta plus 2 sine 4 theta cos theta minus 2 sine theta cos 4 theta. On the bottom we've still got this bit, so on the bottom we still have 5 minus 4 cos 4 theta, and that almost looks similar to what we have here. So if we factorize out the 2 on the top, you'd find s to equal 4 times by sine theta plus 2 lots of sine 4 theta cos theta minus sine theta cos 4 theta. On the bottom we have 5 minus 4 cos 4 theta. Okay, now here you'd have to be careful. If you go to the formula book, we'd have to use our trigonometric identity here. Sine of a minus b is equal to sine a cos b minus cos a sine b. And the reason I say minus is because we have a minus here. Essentially you can think of a to be 4 theta, b to be theta. So we have s, which is equal to 4 sine theta plus 2 lots of sine of 4 theta minus theta. Okay, so that's using the known identity. And then we divide by 5 minus 4 cos 4 theta. So essentially this bit is exactly the same as this bit. And therefore we have 4 sine theta plus 2 sine of 3 theta over 5 minus 4 cos 4 theta, which, if you go back, that's exactly what we have here. So quite a difficult question in my opinion to understand what's going on, but hopefully going through it step by step made complete sense. In terms of the fourth question, part A was, surprisingly to me at least, done pretty well, because I struggled with this part of the question. But a lot of people recognised that you had to use this over here, the sum to infinity. But overall, part A was done pretty well, and eventually you can achieve this result. But part B, that was quite tough. There were incorrect attempts. Basically, a lot of people started using the exponential form. I thought that was quite difficult. But it says interestingly here, the alternative of converting to trigonometric form and then rationalizing was successful for some, but there were often slips in the multiplication, and some were unable to use the correct addition formula to reach the printed answer. I think personally, if you convert to the trigonometry form, that makes life easier, and then you can rationalize everything. And I think the way I set everything out made complete sense. But part B was quite difficult. Question number 5. An engineer is investigating the motion of a sprung diving board at a swimming pool. Let E be the position of the end of the diving board when it is at rest in its equilibrium position, and when there is no diver standing on the board. A diver jumps from the diving board. The vertical displacement h centimeters of the end of the diving board above E is modelled by the differential equation 4 lots of dh squared over dt squared plus 4 lots of dh over dt plus 37h equals 0, where t seconds is the time after the diver jumps. We have to find a general solution of the differential equation. So, first things first, finding the auxiliary equation. We have 4m squared plus 4m plus 37 equals 0. Solving this auxiliary equation, you'd find m to equal minus 0.5 plus minus 3i. We have complex roots, and therefore the general solution will be of the form e to the power of minus 0.5t lots of a cos 3t plus b sin 3t. It's a fairly standard thing to find. Now for part B, when t equals 0, the end of the diving board is 20 centimeters below E and is moving upwards with the speed of 55 centimeters per second. We have to find, according to the model, the maximum vertical displacement of the end of the diving board above E. Well, first of all, when t equals 0, h equals negative 20 if we take upwards as positive. The reason being is that's because the end of the diving board is 20 centimeters below E. So, for part B, when t equals 0, h is equal to minus 20, and we can use this to find out the value of A. So we have e to the 0 lots of a times by the cosine of 0 plus b times by the sine of 0 equaling negative 20. This term disappears. E to the 0, that's just 1. So we have a times by 1 times by 1 equals negative 20. A is equal to negative 20. And for the second part, we know the rate at which the diving board is moving upwards. That's at a rate of 55 centimeters per second. So what we'd have to do here then is to first of all work out the second derivative and then use that to find out what b is. So first of all, working out dh over dt, if we differentiate this function, it's a fairly standard thing to differentiate. That would be minus 0.5e to the minus 0.5 t lots of a cos of 3t plus b sine of 3t, and then we have e to the 0.5t lots of minus 3a times by the sine of 3t plus b times by plus 3b times by the cosine of 3t. It's a fairly standard thing to work out. Now we know that when t equals 0, dh over dt is equal to 55. It's moving upwards at that speed. So if we substitute in what we know, we have minus 0.5 e to the 0 lots of a cos 0 plus b sine of 0 plus e to the 0.5t lots of minus 3a sine of 0 plus 3b cos of 0, and this is equal to 55. So we have minus 0.5 lots of a, so we have minus 0.5 a, and then here we have sorry, this is just e to the 0, and then here we have 3b. Okay, and we know that this is equal to 55, and we know that a is equal to minus 20, so we have minus 0.5 times by minus 20 plus 3b equals 55. So we have 10 plus 3b equals 55. 3b is equal to 45, and therefore b is equal to 15. Okay, so having said that, we can therefore find out the particular solution of h to be e to the power of 0.5t lots of minus 20 cos 3t plus 15 sine 3t. Okay, and also we can find out the particular solution of the speed. So we can conclude that dh particular solution over dt is equal to minus 0.5 e to the minus 0.5t times by minus 20 cos 3t plus 15 sine 3t plus e to the minus 0.5t lots of, well, here if you go back, we have minus 3a, so we have minus 3 times by minus 20, so that's positive 60. So we have plus 60 sine of 3t, and then we have 3b as well somewhere. So we have 3 times by 15, which is 45. So we have 45 cos 3t. Okay, so for the remainder of the question, we have to find the maximum displacement of the end of the diving board above E. So this is a fairly standard differentiation problem in that now we have to set this thing equal to 0. So now we would have to work out, well, if we set this thing equal to 0 to find the time, we can substitute that time back into here to find the maximum displacement. And the reason I want to set dh over dt equal to 0 is because we have to find the maximum vertical displacement. Okay, so we have to use our differentiation knowledge. So doing that, we set this entire thing equal to 0. So let's just highlight this, copy, and then paste. So this thing, if I move this up a bit, is equal to 0. So well, first thing we can do is we can multiply this minus 0.5 into the bracket. So we have e to the minus 0.5t, minus 0.5 times by minus 20, that's 10. So we have 10 cos 3t, and then here minus 0.5 times by 15, that's minus 7.5. So we have minus 7.5 sine 3t. And then we have e to the minus 0.5t, lots of 60 sine 3t plus 45 cos 3t equals 0. And if we collect like terms, in terms of cosines, well, we can factorize out from both sides, from both brackets, in e to the minus 0.5t, and then inside the bracket we have 10 cos 3t plus 45 cos 3t, so that's 55 cos 3t, and then 60 sine 3t minus 7.5 sine 3t, that would be 52.5 sine 3t. Okay, and this of course is equal to 0. Now we should know that e to the minus 0.5t cannot equal 0, and therefore we have 55 cos 3t plus 52.5 sine 3t equals 0. And if we solve this equation, first of all, sine 3t over cos 3t is equal to minus 55 over 52.5. So here we get 22 over 21. So we have tan 3t equals minus 22 over 21. 3t is equal to the inverse tangent of minus 22 over 21, and then obviously we'd have to add on pi. So 3t, we can work out that value. So to work out that value, we have the inverse tan of minus 22 over 21 plus pi. We have 2.3329, etc. And therefore t is equal to, if I divide this by 3, 0.7776, etc. seconds. Now we wish to find the maximum displacement, so we have to substitute this value of t back into our h. So when t is equal to 0.77, etc. H is equal to e to the power of minus 0.5 times by 0.77, etc. multiplied by minus 20 cos of 3t, so we have minus 20 cos of 2.33, etc. Plus 15 sine of 3t, so we have 15 sine of 2.33, etc. So h, therefore, if we work this out, we have e to the minus 0.5 lots of this, lots of minus 20 cos of 3 lots of this, plus 15 sine of 3 lots of this. H is equal to 16.715, etc. So therefore H, the maximum displacement, H max, is equal to 16.7 centimeters to 3 significant figures. Okay. And now for part C, we have to comment on the suitability of the model for large values of t. So the value of h is very small when t is large, and this is likely to be correct, and that's because the displacement of the board should get smaller, suggesting that the model is. In terms of question 5, which was a modelling question regarding second order differential equations, part A was done pretty well. The correct form of the general solution was widely seen, although the h equals something was sometimes missing, or y or x were used instead of h and t. Part B, there were common errors in part B. A lot of people used h equals 20. You were supposed to use h equals minus 20, and I discussed that in the question. And then you can work your way through this question. But the more sensible approach to solving for t was to use sine 3t over cos 3t equals this quantity. And even then, once you reach this step, people forgot to add on the result of pi, and that's mentioned here. The other problem, people were working in degrees. Remember, when differentiating or integrating with sines and cosines, or any sort of trig, you have to use radians. And if you use degrees, you obtain a very unreasonable value for h max. Part C, that was done pretty well, but these questions, when it says talk about the suitability, make sure you talk about the suitability. A lot of people didn't talk about that, and I discussed this question in detail. Question number 6. In an Argand diagram, the points A, B and C are the vertices of an equilateral triangle with its centre at the origin. The point A represents the complex number 6 plus 2i. We have to find the complex numbers represented by the points B and C, giving it answers in the form x plus iy, where x and y are real and exact. This is a fairly complicated question. So, to begin with, we have to note the following. So, if z1 is one root of the equation z to the power of n equals s, and 1 omega squared etc. up to omega to the power of n minus 1 are the nth roots of unity, then the roots of z to the power of n equals s are given by z1, z1 omega squared etc. up to z1 omega to the power of n minus 1. And this process of multiplying the roots by omega, that's the same as rotating z1 about the origin by a certain angle, and it depends on the information you've been given to work out that angle. Now, of course, we've got 3 points on the triangle, okay? And if we've got 3 points, that means somewhere we've got a cube root of an equation, okay? Hopefully this should make sense. So, what's the best way of explaining it? You'll notice that the vertices of the triangle, so the vertices of the triangle correspond to the cube roots. Correspond to the cube root of 6 plus 2i cubed. So if we cube root this, of course, one of the roots we'll get is 6 plus 2i. But we've got 2 other roots as well that we need to work out in this question. And of course, those roots will be complex. Okay, hopefully that makes sense. And essentially, going back to what we have over here, we can find those cube roots by multiplying 6 plus 2i by the cube roots of unity. Okay, so let's just write that down. Hence, we can find the roots by multiplying 6 plus 2i by the cube roots of unity. And this is the same as rotating z1 about the origin. Okay, so which is the same as multiplying 6 plus 2i about the origin. Okay, so these explanations I've given is something which is vital that you know. Now, the cube roots of unity are 1, omega, and omega squared. Okay, because we've got 3 points on a triangle, so these are our cube roots of unity. And you'd find over here omega is equal to e to the power of 2 pi I over 3. Okay, so so let's just move that here. So hopefully this makes sense so far. Now, if we consider this 6 plus 2i, we can write that in an equivalent form. If we have 6 plus 2i, we can find the modulus and the argument of that. Okay, so if you go to your calculator and then go to the complex mode, if you type in 6 plus 2i, and then if you press options, the argument, press number 1. Over here, what we can do then is if you type in options and then number 1 for argument, the argument is 6 plus, we want to find out the argument of 6 plus 2i, which is 0.321, etc. I prefer to leave that in exact form instead. And the exact form is the inverse tangent of 2 over 6, which is the same as the inverse tangent of a third. However, for the modulus is equal to actually, let's write this out in full. The modulus of 6 plus 2i is equal to 6 squared plus 2 squared square rooted, which is root 40. Okay, and the argument of 6 plus 2i, that's equal to the arctan of 2 over 6, which is the same as the arctan of 1/3. Okay, and therefore what we can conclude from here then is that we have root 40 times by e to the power of I times by the arctan of 1/3. Okay, so this thing here is the same as 6 plus 2i. Okay, hopefully, if I highlight this thing here is exactly the same as this complex number. Now, from this we can find out the vertices. Okay, so if we wish to find the vertices, the vertices are, well, we've got to use this statement here, where we multiply 6 plus 2i by the cube roots of unity. So we've got one vertice, which we'll do in red, at root 40 e to the power of I times by the arctan of 1/3, which is 6 plus 2i. We already know that. Okay, now for B and C, that's a bit more complicated. First of all, from here it should become quite obvious that the coordinates of A will then be 6, 2. If we now consider the other root, we have root 40 times by e to the power of I arctan of 1/3, and then we have to multiply this by the cube root of unity over here. We have to multiply by this thing, e to the power of 2 pi I over 3. Okay, let's just write this all in a consistent form. And what this is the same as is, if we write this down, this is the same as root 40 e to the I of the arctangent of 1/3 plus 2 pi over 3. Okay, now 2 pi over 3, that's 120 degrees. So what this is the same as, if we consider this statement here, where we this is the same as, rather, this should be rotating. this over here is the same as rotating. So this bit is the same as rotating this about the origin. This thing over here then is the same as rotating 6 plus 2i by 120 degrees, or 2 pi over 3 radians, about the origin. Okay? So, for us to rotate a point about the origin, if we go back to our formula book somewhere, under the matrices section, here, when we rotate something anti-clockwise, we'd have to use this over here. So it's quite complicated to do this, but this coordinate would have to rotate by 120 degrees. Okay? So we have then cos of 120 minus sine of 120, sine of 120 cos of 120 multiplied by this coordinate 6, 2. And if we work this out, we have 6 times by the cosine of 120 minus 2 times by the sine of 120, and then we have 6 times by the sine of 120 plus 2 times by the cosine of 120. So if we work out this vector, if we go to our calculator, make sure that you're in degrees mode if it helps. We have 6 times by the cosine of 120 minus 2 times by the sine of 120. That's minus 3 minus root 3. And for the other part, we have 6 times by the sine of 120 plus 2 times by the cosine of 120. We get minus 1 plus 3 root 3. Okay? And therefore, the coordinates of B are minus 3 minus root 3 plus minus 1 plus 3 root 3 I. And we'd have to do the same thing with the other coordinate. So if we do the next bit in green, we now have to consider multiplying this by omega squared, which is consistent with what I said here. So we would now have to, if we consider the other coordinate, we have root 40 e to the I times by the inverse tangent of 1/3, and then we multiply this by e to the I 2 pi over 3 squared. Okay, so what this is equal to then is root 40 e to the I, now 2 pi e to the I 2 pi over 3 all squared. that's e to the 4 pi over 3. So we have ei to the arc tangent of 1/3 plus 4 pi over 3. Okay? So what we're doing over here then, 4 pi over 3, that's 240 degrees. So this is the same as rotating this 0.6 plus 2i by 240 degrees, or if you want to leave that in radians, 4 pi over 3 radians about the origin. Okay? So this bit therefore is consistent with what I said over here. Okay? So we would now have to work all this out. So we have the cosine of 240 minus sine of 240, sine of 240, and cosine of 240 multiplied by 6/2. We need to work this out. So going back to our calculator, here we have 6 times by the cosine of 240 minus 2 times by the sine of 240. Okay, and then for the other coordinate we have 2 times by the sine of 240. Sorry, we have rather 6 times by the sine of 240 plus 2 times by the cosine of 240. Okay, so if we work this out, we have 6 times by the cosine of 240 minus 2 times by the sine of 240. You'd find we get minus 3 plus root 3. So we have minus 3 plus root 3. And then we have 6 times by the sine of 240 plus 2 times by the cosine of 240. That would be minus 1 minus 3 root 3. Okay? And therefore, the coordinates of C would be minus 3 plus root 3 sorry, as a complex number, C is equal to minus 3 plus root 3 plus minus 1 minus 3 root 3 I. So that was a fair bit of work to do for part A. Okay, so that's of the correct form in a real and exact form. It's a lot of work for 6 marks, I thought. And the points for part B, the points D, E and F are the midpoints of the sides of the triangle ABC. We have to find the exact area of the triangle DEF. So for part B, I've just drawn out the triangle ABC showing the midpoints D, E and F. I've also shown the coordinates of A, B and C. And we know that D, E and F are the midpoints of the sides. So in this question, we want to find out the area of the triangle. And the triangle we're interested in is this triangle here. So if I just join everything up, we're interested in working out the area of this triangle here, 60 degrees here, 60 degrees here, 60 degrees here. The reason for that, we have an equilateral triangle, and therefore, because DE and F are the midpoints of these sides, DE, EF and DF are all equivalent in length. If we find out these midpoints, first of all, let's find out the midpoint of AB. So we have minus 3 plus 6 minus root 3, and then divide that by 2. So we have 3 minus root 3 over 2. And then, in terms of the other coordinates, 3 root 3 minus 1 plus 6 all over 2. We have 3 root 3 plus 1 over 2. Okay, so let's just move this coordinate, let's just move this a bit down here. Okay, so that here I've just shown the coordinates of D. Working out the coordinates of F, the midpoint of this, 6 plus root 3 minus root 3, and then divide that by 2. We have 3 plus root 3 over 2, and then 2 minus 1 minus 3 root 3, and then divide that by 2. We have 1 minus 3 root 3 over 2. And for E, we have minus root 3, minus 3 minus another 3 minus root 3 plus root 3, and then divide that by 2. We have minus 3, and then here 3 root 3 and minus 3 root 3 cancelled, minus 1. Here we just get minus 1. Okay, minus 1 plus minus 1 over 2. Okay, so we've now worked out the coordinates of D, E and F, and the next thing to notice, because we have an equilateral triangle, DE equals EF equals FD. Okay, so we can actually find out the length using the length formula. So if we consider these coordinates here, we have 3 plus root 3 over 2 minus 3 minus root 3 over 2 squared, plus, in terms of the other coordinates, we have 1 minus 3 root 3 over 2 minus 3 root 3 plus 1 over 2. Okay, square root, and then we square root this. Okay, so let's just square root. So if we work this out, on the top we end up with root 3. So we have root 3 squared. Just move this bit here. And then here we have minus 3 root 3. So plus minus 3 root 3 squared. And then we square root this. So if we work this out, we have 3 plus 27 square rooted, which is root 30. So what does that mean? We have root 30 here, root 30 here, and root 30 here. And now we have to use, well, we can quite easily find out the area. The area of the triangle DEF, we have a half AB sine C, so we have a half times by root 30 times by root 30 times by sine 60. So if we work this out, you'd find the area to equal 15 root 3 over 2 units squared. Okay. Question 6 was a quite difficult question. People were very poorly prepared for this question, and I think this is one of those topics which you have to know the textbook inside out before you attempt this paper, or at least the examples from the textbook. But essentially you had to use the cube roots of unity to do this question. Those that use the matrix method, which is what I did over here, usually obtain the correct answer. And I thought this question was quite difficult because you can't just stick all this into your calculator and get the right answer, because the question said something about leaving everything in exact form. There were other weaker attempts which included a reflection of 6, 2 in the coordinate axis, but you can't do that because you've got 3 roots, so it forms a triangle. And in terms of part B, that was a quite difficult question for a lot of people. I thought it was straightforward if you draw a diagram and then you can figure out how to find out the area of the triangle. Some use the half times base times by height approach rather than half AB sine C. That was quite difficult. But if you use the coordinates to sketch out a diagram, you can do this question pretty well. And don't forget, you have to state your units. And the other thing which is worth mentioning is make sure that you can use your rules of thirds properly. Again, a lot of this goes down to your understanding of A-level maths. Question number 7. The matrix M, which is equal to 2 minus 1, 1, 3, k, 4, 3, 2, minus 1, where k is a constant. We have to find the values of k for which the matrix M has an inverse. Well, singular matrices do not have an inverse. In other words, the determinant of M is equal to 0. So if we solve and form an equation for k, we can find out the value of k, and then k doesn't equal that value for M to have an inverse. So if we work out the determinant of M, well, what we do is, if we go along the first row, we look at this 2, and we go across, and then we work out the determinant of what's left. So we have 2 lots of k, 4, 2, minus 1. Okay, and remember the order of signs. We have plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay, so for the next entry we have minus, and then if I just get rid of this, we now look here, we delete across, we delete down, so we have 3, 4, 3, minus 1. So we have minus, minus 1, lots of 3, 4, 3, minus 1. And then we have plus. So if I get rid of this, if we look here and delete like that, we have 3k, 3, 2. So we have 1 lots of 3k, 3, 2, and all this is equal to 0. Okay, so if we work this out, we have 2 lots of, well, here we have minus k minus 8, and then we have plus 1 lots of minus 3 minus 12, plus 1 lots of 6 minus 3k, and this equals 0. Okay, so if we expand and simplify, we have minus 2k minus 16 minus 3 minus 12 plus 6 minus 3k equals 0. So we have minus 5k minus 25 equals 0, and you'll notice over here the determinant of this matrix M is equal to minus 5k minus 25. So it follows that k is equal to minus 5, and therefore we can conclude from here that the matrix M has an inverse when k doesn't equal minus 5. Okay, so it doesn't have an inverse when k equals minus 5, and therefore it has an inverse when k equals minus 5. For part B, we have to find in terms of P the coordinates of the point where the following planes intersect. So for this question, we've got these three equations, which if we write all these in an equivalent form, we have the matrix 2 minus 1 1, 3 minus 6 4, 3 2 minus 1 multiplied by x y z, and this is equal to p1 0. So for this part, to find out the values of x, y and z, we would have to find the inverse of this matrix and multiply it by p. So x, y, z is equal to 2 minus 1 1, 3 minus 6 4, 3 2 minus 1 inversed multiplied by p1 0. So if we work out that inverse matrix, so go to menu, matrix, we will define matrix A with 3 rows 3 columns with entries 2 minus 1 1, 3 minus 6 4, 3 2 minus 1. Okay, and if you press AC and then go to options, and then if we have matrix A and then find the inverse of it, well, we can factorize out a 1/5. So we have 1/5, and then here we have minus 2 1 2, and then if I factorize out the 5th, then here we'd have 15, because 15 times by a 5th gives us the 3. Here we have minus 5, because a 5th times by minus 5 is minus 1. Then we have minus 5 again, and then here we have 24 minus 7, and then minus 9. Okay, and then we multiply this by p1 0. Okay, so if we work this out, well, we'd still have this 1/5, and essentially we go across and then down, so we have minus 2 times by p, 1 times by 1, and then we have 2 times by 0, and then for the next row we have 15 times by p, minus 5 times by 1 minus 5 times by 0. And then we have 24 times by p minus 7 times by 1 minus 9 times by 0. And therefore, in terms of coordinates, we'd have minus 2p plus 1 over 5. And then we have 15p minus 5 over 5, which is 3p minus 1. And then we have 24p minus 7 over 5. So those are the coordinates. Okay. So for this part of the question, part C, we have to find the values of q for which the set of simultaneous equations 2x minus y plus z equals 1, 3x minus 5y plus 4z equals q, and 3x plus 2y minus z equals 0 can be solved. And for this value of q, we have to interpret the solution of the set of simultaneous equations geometrically. So far I've written down the equations. I've labelled them 1 to 3. And for this question we have to assume some sort of consistency. In other words, a system of linear equations is consistent if there is at least one set of values that satisfies all the equations simultaneously. And for this, various different ways we can try this question. One way is to try to eliminate z. Okay, so we will try to eliminate the variable z. One way we can do that is add equation 1 to 3. So if I add equation 1 to equation 3, 2x plus 3x, that's 5x, minus y plus 2y, that's y, and then we have 1. Okay, 1 plus 0. Sorry, we have z plus minus z, which is 0, and then 1 plus 0, which is 1. We'll call this equation 4. And if I multiply equation 3 by 4, then we have 12x plus 8y minus 4z equals 0. If I call this equation 5, we can now add together equation 2 and 5, which will also eliminate z. So we will add together equation 2 and equation 5. And if we do that, 3x plus 12x, that's 15x, and minus 5y plus 8y, that's 3y, 4z minus 4z, that's 0z, and then we have q plus 0, which is q. Okay. And now what we can do is, if we multiply equation 1 by 4, so if we multiply equation 1 by 4, we have 8x minus 4y plus 4z equals 4. We'll call this equation 7. And if we subtract equation 7, if we subtract equation 2 from 7, that will also eliminate z. So 7 take away 2, we have 5x plus y equals 4 minus q. Okay, so we'll call this equation 8. Okay, so what we can say from here then is we have this 5x plus y equals 1 and 5x plus y equals 4 minus q. So if we set equation 4 equal to 8, we have 1 equals 4 minus q, from which we see q is equal to 3. And if we compare equation 6 over here. If we compare equation 6 with equation 4, then what you'd find then is equation 6 is equal to 3 times by 4, and therefore Q is equal to 3. Okay, so Q is equal to 3. Now what does this mean? Well, it means that the planes form a sheaf. In other words, the plane intersect at a line. Let's just show that. So the three planes, there are 3 planes that form a sheaf. In other words, the 3 planes that meet, that intersect at a line. Okay, and they look something like that. Question 7 was a matrices question, part A. There were slips in finding out the determinant. A lot of people gave this answer of k equals 5 but failed to recognize that the question requires the values of k for which the M1 had in, for the matrix M had an inverse, and not the value of k for which M was singular, so you have to say k doesn't equal minus 5. Part B, that was talking about the intersection of 3 planes, and the way you can approach this question to find the inverse, of course you can use a calculator. There's nothing stopping you. Look at the amount of marks this question's worth. There's nothing stopping you using a calculator. And part C, that people in terms of interpreting this question geometrically. But there were just common slip-ups and sign errors, etc. But overall, this question I thought was a fairly easy question for this paper. Question number 8. Figure 1 shows the central vertical cross-section ABCD of a padding pool that has a circular horizontal cross-section. Measurements of the diameters of the top and bottom of the padding pool have been taken in order to estimate the volume of water that the padding pool can contain. Using these measurements, the curve BD is modelled by the equation y equals the natural log of 3.6x minus k, where x is in between 1 and 1.18, as shown in figure 2. We have to find the value of k. Well, if we use this coordinate here of 0 across, 1 across 0 up, for part A, using x equals 1, y equals 0, we have 0 equals the natural log of 3.6 times by 1 minus k. And if we antilog both sides, we have e to the power of 0 equals 3.6 minus k. So therefore k is equal to 2.6. And therefore y is equal to the natural log of 3.6x minus 2.6. We'll call this equation 1. For part B, we have to find the depth of the padding pool across according to this model. Well, let's see what happens when x equals 1.18. For part B, when x is equal to 1.18, we have y equals the natural log of 3.6 times 1.18 minus 2.6. So if we work this out, we have the natural log of 3.6 times 1.18 minus 2.6, which is this value of 0.4995, etc. And so therefore the depth is equal to 5.00 meters to 3 significant figures. For part C, the pool is being filled with water from a tap. We have to find, in terms of h, the volume of water in the pool when the pool is filled to a depth of h meters. Well, clearly, to make this shape, we have to rotate this line BD about the y-axis to find the volume. So when we rotate about the y-axis, so if we have a rotation about the y-axis, we have pi lots of the integral of f of y squared dy. And if we take a look at equation 1, if we have x equals, well, I think a better way to write this actually would be to rewrite this as x squared dy. If we take a look at equation 1, we can rearrange to find what x is in terms of y and then square that result and stick it back into here. So from equation 1, we have e to the power of y equals 3.6x minus 2.6, from which we can see x is equal to e to the power of y plus 2.6 over 3.6. We'll call this equation 2. And therefore, we can quite easily work out the volume. And we're finding out the volume in terms of h. So we're integrating from, if you go back here, from 0 to some point h. Okay? So we can see that the volume is equal to pi lots of the integral from 0 to h of this thing squared. So we have e to the power of y plus 2.6 over 3.6 squared dy. So this is equivalent to pi over 3.6 squared lots of the integral from 0 to h of e to the power of y plus 2.6 squared dy, which is equivalent to pi over 3.6 squared times by the integral from 0 to h of e to the power of 2y plus 5.2 e to the power of y plus 6.76 dy. And if we work this out, we have pi over 3.6 squared lots of well, here we have 0.5 e to the power of 2y plus 5.2 e to the power of y plus 6.76. Okay, and we want to evaluate this between 0 and h. So we have pi over 3.6 squared lots of, for our upper limit we have 0.5 e to the 2h plus 5.2 e to the h plus 6.76 h. And for our lower limit we have 0 plus, sorry, for our lower limit we have 0.5 plus 5.2. Okay, so therefore it turns out we get pi over 3.6 squared lots of 0.5 e to the 2h plus 5.2 e to the h plus 6.76 h minus 5.7. Okay. If you want, let's see what happens if we expand and simplify. So we have 1 over 3.6 squared multiplied by a half. So we get pi lots of 25 e to the 2h over 648. And then we have 1 over 3.6 squared multiplied by 5.2. That would be 65 e to the h over 162. And then we have 1 over 3.6 squared multiplied by 6.76. That would be 169h over 324. And then we have 5.7 multiplied by 1 over 3.6 squared, which is 95 over 216. So, sorry, this is in meters cubed. So this is our volume in meters cubed. Okay. Fair bit of work that. Now for the next part, given that the pool is being filled at a constant rate of 15 litres every minute, we have to find in centimetres per hour the rate at which the water level is rising in the pool when the depth of the water is 0.2 meters. Well, when the depth is 0.2 meters, we can use that information to find out what the volume is. Actually, it was a better way of phrasing this question. Well, if you think about this question for part D, we're finding out what dH over dt is. And we also know that dV over dt is equal to 15 litres per minute. And we can use the fact that dH over dt is equal to dH over dV, lots of dV over dt, to find out what dH over dt is. So let's begin by finding dV over dH. Okay. That will just be this bit over here, won't it? So if we integrate this, if we differentiate this bit, we can find out what dV over dH is. We'll do this in a different colour. dV over dH is equal to pi over 3.6 squared lots of e to the power of 2h plus 5.2 e to the power of h plus 6.76. Okay, and when h is equal to 0.2, we can substitute this into here to find out what dV over dH is. So we have pi over 3.6 squared lots of e to the power of 2 times by 0.2 plus 5.2 times by e to the power of 0.2 plus 6.76. So dv over dh, let's work this out. So we have e to the power of 2 times by 0.2 plus 5.2 e to the power of 0.2 plus 6.76. We divide this by 3.6 squared, and then we multiply this by pi. So we get a value of 3.539, etc. liters per minute. Okay, now we want to work out what dH over dt is. So dH over dt, that's equal to dH over dv multiplied by dv over dt. So dH over dt, that's the inverse of this. So we have 1 over 3.539, etc. And then we multiply this by, well, here if you go back, we have 15 liters per minute. So we have 15 over 1000 multiplied by 60. So if we work this out, so we have 1 over this multiplied by 15 over 1000 multiplied by 60, which is 0.254, etc. So we have 0.254 centimeters per hour to 3 significant figures. Okay. Question 8 was basically an integration question, volume of revolution question. This question surprisingly challenged many. This topic used to be on the regular A-level maths spec of the old spec, so I thought it was a pretty easy question. Part A, most were able to use the model with x equals 1 and y, which is good. Part B, a lot of people were unable to recognize that you had to use this 1.18. And then for the part C, a lot of people recognized that you had a volume of revolution question. So at some point you have to rearrange for x and then substitute back into here. But there were a lot of errors in terms of the algebra in this question. And even in terms of the limits, there were a lot of slips, and you have to just make sure that you recognize everything makes sense if you look at the diagram. So just make sure that you pay attention to your limits. But part D, which again is from your regular A-level maths in my opinion, that's just a standard chain rule question. It wasn't a difficult question. A lot of people failed to recognize that you had a chain rule question. Weaker attempts tended to involve calculating V and then attempting to adjust its value. I don't know why people do that. Many otherwise successful candidates were unable to correctly manage the different units used in this question. So I think there was something about minutes and seconds or something, or minutes and hours. Candidates were able to deduce that the rate of change of h with respect to time was proportional to the circular surface area of the pool, and correctly proceeded without any further calculus. Okay, so I didn't do that, but I guess that's one way. I just used the chain rule method, which I thought was quite obvious.